The universe is made of matter. 98% of this matter, ignoring the dark matter, is pure hydrogen and helium. But, thankfully, billions of years ago, supergiant stars fused the hydrogen and helium into all the other elements and then exploded them all over the universe. And that's where chemistry came from. These elements grouped together into a vast array of different molecules, and these molecules combined with each other in a stupendous number of complicated ways. Chemistry is the subject that studies this matter in all of its forms and how it all interacts. It goes from simple atoms right through to complex biological molecules like proteins and DNA. It's a huge, fascinating and complex subject, and this video is all of that condensed. Humans have had an interest in chemistry for a very long time. We wouldn't be what we are today if it was not for the chemical reaction of fire. We used this to develop other chemical techniques, from cooking food, making metal from ores, or making glass, amongst many others. Since then, many advances in human civilization have been built on the back of advances in chemistry, like metalworking, or manufacturing fertilizer, or making new materials and drugs. Let's look at what falls under the umbrella of chemistry. First, there's matter, and all the different things that matter's made of. At the very smallest scale, we start with atoms and the periodic table that organises all of the different types of atom, called chemical elements. Elements in each column have similar chemical properties. Atoms are made of protons and neutrons in the nucleus with electrons surrounding them, and most of chemistry is due to how these electrons behave. By joining together atoms, you get molecules, and different kinds of molecule are called chemical compounds. Chemical compounds usually have very different chemical properties to the elements that they're made from. Think about it. Hydrogen is very explodey, oxygen is very burny, but combine them together into H2O and you get water, the least explodey, burny thing around. Compounds don't have to be made of single molecules. Many solids, like metals or salts, have a crystal structure made of repeating groups of atoms called unit cells. If you have several substances together, you have a mixture, like the air around you or a cake. Now let's move on to how atoms stick together with a very important subject of bonding. Atoms bond together in several different ways, where they reduce their combined energy by stealing or sharing electrons, or moving them into different configurations. A universal rule in science is that everything is always trying to minimize their energy, and bonding is one way that atoms achieve that. Understanding how energy moves around in chemical substances is vital to understand when reactions will or will not happen. For example, wood won't react with oxygen to start burning spontaneously, but if you give it enough energy to begin with, it will. Another example where energy is very important is where you can speed up a reaction between two other compounds by introducing a catalyst, and the catalysts make it more energetically favourable and so speeds up the reaction. Energy also determines when compounds will exist in the different forms, solid, liquid or gas. Which form they'll be found in comes from the temperature that they're at and the pressure that they're under. The values vary for each material, but in general things are solid at low temperature and or high pressure, and gas at high temperature and low pressure. Another really interesting form of matter is a plasma, which is where you rip the electrons off atoms in a gas to make them into ions. This is what's used to make neon lights. Chemical reactions form the core of chemistry. Which compounds react with each other, why they react, and what is left over after a reaction. There are many different kinds of reaction which can be categorized in different ways. All of these reactions are governed by a set of fundamental rules called chemical laws, the foundation of which is the conservation of mass and energy, which means that no matter or energy is created or destroyed in a chemical reaction, they just change to different forms. Kinetics is the study of how fast reactions happen and the things that control what the reaction rates are. A reaction where electrons are transferred from one reactant to another is called an oxidation-reduction reaction, or a redox reaction for short. Oxidation means a loss of electrons from a substance, and a reduction means the gain of electrons, and they have to happen together. An example is sodium and chlorine. Chlorine is the reducing agent and sodium is the oxidizing agent. Another important property of substances is their pH, whether they're an acid or a base. There are several theories to model acid-base reactions, but one way to think about it is that acids are substances that have a hydrogen ion ready to give up in a chemical reaction, and a base is a substance that takes a hydrogen ion. If there are a number of different chemical compounds which can react with each other back and forth, there can be swings between one substance and another. Equilibrium is where the amount of each substance is constant, even though a reaction may still be taking place. This can also happen in phase changes, like from solid to liquid or liquid to gas. So those are the basics of chemistry. Research in chemistry looks at how these rules apply in different chemical systems. So now I'm going to move on to look at the different fields in chemistry. Theoretical chemistry attempts to explain the structures of atoms and molecules and how they interact using mathematical methods. It's very closely related to theoretical physics and quantum chemistry, and often uses techniques in computational chemistry where atoms, molecules, and reactions are simulated in a computer. Now, simulating the proper quantum behavior of anything more complicated than a single hydrogen atom is very difficult/impossible for multiple bodies. So many cutting-edge techniques in computer science are used to try and simulate molecules and how they interact with each other. In fact, this is one of the most exciting applications of quantum computers because they'll be able to directly simulate chemical systems and will help with things like discovering novel materials and drugs and a whole lot more. Physical chemistry studies chemical systems in terms of their physics, so things like energy, force, time, motion, thermodynamics, quantum properties, amongst others. There are many subfields, like looking at the electronic properties in electrochemistry, which is important for developing better batteries, or materials science, which is trying to create materials with new properties like extreme strength, durability, or self-healing. This is a critical problem with building Earth-based nuclear fusion reactors which are reliant on new materials. Analytical chemistry is like detective work. You've got a sample of something and you need to work out what it's made of and the amount of the different components. Chemists have developed a huge array of techniques to probe and measure different properties of different materials. Traditional techniques involve wet chemical techniques like precipitation, which separates compounds depending on what temperature they evaporate. There's also a huge array of modern techniques like chromatography, where different compounds move at different speeds through a solution and so separate. Or the many different kinds of spectroscopy that can detect materials by shining light on them, or mass spectroscopy, where the materials are flung through electric or magnetic fields to separate them according to their masses. And finally, we get to the huge fields of inorganic, organic, and biochemistry. Organic and biochemistry look at the chemistry of living things, and inorganic chemistry looks at everything else, although there is still a large amount of crossover. Most of the inorganic compounds that are studied are man-made, and a lot of the motivation is to find chemicals with new properties that can be used in the chemical industry in the wider world. In fact, there are very few areas of human endeavour where inorganic chemistry has not been used in some way. There's medicine and agriculture, special fluids like detergents or emulsifiers, special coatings, materials, pigments, or fuels for many industrial purposes. Within chemical production itself, catalysts are very important as they speed up other chemical reactions. Inorganic chemistry also bleeds into material science, making solids with novel crystal structures like high-temperature superconductors, for example. The list is endless. Now, between inorganic and organic chemistry sits organometallic chemistry. This looks at organic compounds which are bonded with a metal, and are typically used in reactions in the chemical industry, often as catalysts. Organic chemistry looks at the structure and behaviour of the molecules of life, which are typically built from a small set of different atoms: carbon, hydrogen, oxygen and nitrogen, plus a few others. Organic chemists also look at making new organic compounds with useful properties. Organic molecules all contain carbon, and the carbon-hydrogen bond is the most common structure in organic chemistry. There are a huge number of applications of organic chemistry in industry: fertilizers, pesticides, lubricants, polymers, and plastics. And in the consumer world, there's fragrances, flavorings and preservatives, and of course drugs in the pharmaceutical industry. And finally, out of organic chemistry comes biochemistry, which studies the chemistry of living organisms. Biochemistry studies components that can be inorganic, like water or minerals, but also looks at the biggest and most complex molecules like proteins, fats, and DNA. At the other end, this field also blends into molecular biology, which looks in the finest detail at how life arises out of the chemical processes inside cells. Within biochemistry, there are four main classes of molecules called biomolecules. Carbohydrates are used for structures and storing energy, lipids, which make up fats, proteins, which are very large molecules made from amino acids that have a huge array of different functions in the body, and nucleic acids that are used to convey genetic information. Research in biochemistry has had a huge impact on medicine, helping us understand infectious and genetic diseases, improving organ and tissue transplantations, working out what's wrong with you with clinical diagnostics, and of course understanding nutrition, looking at the functions of vitamins and minerals in our body. Biochemistry has also been very important for agriculture, studying soils, fertilizers, and pest controls, and there's many other applications too. So that is my attempt to summarize all of chemistry in about 12 minutes. No simple task, as it's so incredibly complicated. It has always amazed me that something so complex as a human is built on a foundation of a huge number of simple chemical reactions. Your consciousness right now is a function of the chemistry going on in your brain cells, oxygen being passed from your blood and sugars being metabolized inside them. Chemistry spans a huge mountain of complexity from a single atom to the cells that keep you alive, and I find it endlessly fascinating.